All right, this question says, two progressive sound waves, y and z, meet at a fixed point P. The variation with time t of the displacement x of each wave at a point P is shown. So we know they're sound waves, they're progressive, they transfer energy. Use this figure to state one quantity of the waves that is the same and one that is different. Okay, well, we could read off the period of this wave because time is plotted on the x-axis. You could see that the period of this wave y is 3 seconds. If we start here at 1 second, where this wave starts, and we go up, down, and then it repeats again right here at 4 seconds, you see how this wave has exactly the same time period of 3 seconds? So they have the same period, it's just they're out of phase. It's like this wave doesn't start where it's rising up above equilibrium at the same time here. It's down like already where it's almost at its trough, where this one is sort of at equilibrium, you know, where we sort of think of the wave as sort of traditionally beginning. But if we look at sort of where we can compare them, we say, okay, well, wait a minute, they have the same period, 3 seconds. So same period. We can quantify it, state its value, 3 milliseconds. What's different? Well, the amplitude, right? So wave y goes up to 4 micrometers and wave z only goes up to 2 micrometers. So the amplitude is different. The phase is different, so they're out of phase, you know, but let's just stick with period is the same and the amplitude is different. Good. State and explain whether the waves are coherent. Well, they're both sound waves. They're both traveling in the same medium, and they have the same time period. They have the same time period. Then they have the same frequency, right? We just do 1 divided by 3 milliseconds. We have the frequency, and we'd realize these have the same frequency. And so this is an example of coherent waves. Waves that have the same frequency and keep the same frequency are coherent. It says to determine the phase difference between the waves, and they want it in degrees. So how can we calculate phase difference? This isn't something that we spent a lot of time dealing with. So how different are these, you know, sort of waves from each other? So if the entire time period is 3 milliseconds, then how far sort of off from the beginning is sort of one wave compared to the next? And so this one is, it shifts by, you know, it's sort of out of phase by sort of 1 second out of the 3 total seconds. So it's like 1/3. So it's a fraction 1/3, but if we multiply that by 360 degrees, then that is 120 degrees. So you can kind of think about phase difference as a fraction, you know, where one total sort of oscillation is one whole phase of the wave. So that's equal to 360 degrees. So if you can figure it out with a fraction and then just multiply it by 360 like we did there. So it was, again, the calculation was 1 millisecond of shift divided by the total time period, 3 milliseconds. So that's 1/3 of 360 degrees, because there's 360 degrees of total phase in a wave, and they want it in degrees. And so that gives us 1/3 of 360 is 120. 120 for that. And then it says the two waves superpose at P. So we apply the principle of superposition, and the algebraic sum of the displacement of the individual waves equals the displacement of the new wave to determine the resultant displacement at time 0.75 milliseconds. So we're going to 0.75 milliseconds, and we're using the principle of superposition. So 0.75 milliseconds looks to be about, so there's 10 squares between here and here, right? 1, 2, 3, 4, 5, 6, 7.5. So we're looking at sort of this point here. How convenient, and that point right there. So this point up here looks to be 4 micrometers of displacement for wave Y. Wave Z is down here. I think that's probably close to 1, right? Because it's going up by sort of like 0.5, 1, 1.5, 2, or actually there's no 1, 2, 3, 4, 5 divisions. And this one looks like it's on the 1. It's on like the second one, or maybe it's a little bit in between that one. So between like the second and third, sort of right in there. So each of these would be what? 0.4, 0.4, 0.8, 1.2, 1.62. So 0.4, 0.8. So yeah, it's about 1. So it'd be minus 1, right? And so you have to subtract it because it's down, it's negative, right? So the sign here sort of indicates that. So 4 micrometers minus 1 micrometer, 3 micrometers. So those waves add up to 3 micrometers, right? We apply the principle of superposition. Sometimes those waves can cancel out, right? We talk about destructive interference. So just like we can take away 1 from this, well, if we would have met up with a trough that was also at, -4, it would have been 0 and 0 displacement, no displacement, right? So on a stationary wave, it's a node, or it's an area of cancellation, like on an interference pattern. The intensity of wave Y at point P is I, determined in terms of the intensity, I, the intensity of wave Z. Okay, so in terms of I, the intensity of wave P, what is the intensity of wave Z? So here we need some key ideas, like intensity is proportional to amplitude squared. We know that the intensity of wave Y is I and its amplitude is 4. Wave Z has an amplitude of only 2. So we want to know the intensity of wave Z. So we set this up like, I prefer to set it up like this. The intensity of Z over the intensity of Y is equal to the amplitude of Z squared over the amplitude of Y squared. And so the amplitude of Z was 2. The amplitude of Y was 4. 2 squared is 4. 4 squared is 16. So the intensity would be 0.25. So even though it's half the amplitude, it's a fourth the intensity, right? Because it goes as the square. So if you compare two things and you half the amplitude, then you 1/2 squared, or you cut the intensity down by a factor of 4. It's a fourth as intense. For a sound wave, that's loudness, right? So it'd be a fourth as loud as the other one. The speed of wave Z is 330. Determine the wavelength of wave Z. So you may recall that we have already calculated, or deduced rather, the time period of each of the waves. We said that was one thing they had in common, was 3, it was milliseconds. Milliseconds, yeah, the micro was the displacement. 3 milliseconds, okay, was the time period. So we can calculate the frequency as 1/3 milliseconds. That means it has a frequency of 333 repeating. If the velocity is the wavelength times the frequency, and the velocity is 330 meters per second, then the wavelength can be calculated by dividing velocity divided by frequency. So it's going to be about 1. Okay? 330 divided by 333.3 0.99 meters. And here you want to be careful about, oh, we should just round this up to 1, but no, that's 2 significant digits, right? So we just sort of leave it like that. All right, let's look at the marks. Do this one, and we add it here, we downloaded it. We have it open already. And there you have it there. Frequency or period, the amplitude, constant phase difference, so they are coherent, 120 degrees, 2 micrometers, 0.25, 0.99. Well done, everybody.